Hello, and welcome to EGR 312, Learning Module 13. In Learning Module 13, we are going to return to Engineering Economy, the blank and Tarkin text. For the last three learning modules, we had covered project management, and so now we're switching back. In today's lesson, we're going to cover chapters 11 and chapters 13. Chapter 11 is replacement studies, and chapter 13 is break-even analysis. These are both fairly short and straightforward chapters. So we'll go ahead and get started. First, let me switch you over here. I'm bringing up the lesson plan today. And in the lesson plan, again, it reemphasizes we're covering chapters 11 and 13. For homework, there is no homework per se for chapter 11. There's actually a lab, and I'll bring that up in a second. And then for chapter 13, there are just four short homework problems. Taking a look at the lab, I've now brought up the, it says, I think it's called Lab 13A. This is a replacement study lab. Again, it's very important that you take your time, go through this lab. I will explain how to do this lab basically while lecturing on the chapter 11. And there are a couple of questions in here, and I have included the solution for this lab as well in your blackboard. Okay, with that, I am going to turn to the first lesson today, and that's on replacement studies in the slideshow. Okay, replacement study. Usually I like to talk about in class, I like to go over things that I have had experience with, and for first couple of years teaching engineering economy, I had never done a replacement study. But I was working down at Mercer Engineering Research Center a couple of years ago, and lo and behold, I ran into a replacement study. One of the units out at the base was wanted some analysis done, and I'm going through it, and I'm saying, hey, this is a replacement study. I've seen this before. So first let me explain here what a replacement study is. The fundamental issue here is that over time, company assets need to be replaced due to reduced performance, altered requirements, obsolescence. Basically, your equipment wears out over time. And so the issue becomes, do I need to replace this piece of equipment? And it says here, a replacement study answers the question of when, not if, to replace. Okay, so the whole idea here is, should I keep this asset that I have, this machine that I have, this process that I have, should I keep it running for the next couple of years, or should I replace it immediately? And it says here, a replacement study is an application of the annual worth method of comparing unequal life alternatives. Okay, so before we actually get into an example, I want to give you a couple of definitions. The first definition is we have a defender. And the defender is the currently installed asset. Again, that asset could be a machine, a building, a process, but that's the defender. It's what's currently in operation. The challenger, on the other hand, is the best alternative to replace the defender. Maybe you've already done an analysis and come up with several options and whittle them down to a single best alternative. And so what we're going to do here is make a comparison between this defender and the challenger. Of course, AW, annual worth, it's the primary economic measure of comparison between the defender and the challenger. Now, of utmost importance is this idea of economic service life, or ESL. And that is the number of years at which the lowest annual worth of cost for an alternative occurs. Okay, you can get so this is really, how long do I hold on to this asset, this machine, this piece of equipment? How long do I hold on to it? If I hold on to it for too long, it's going to cost me a lot of money. If I hold on to it for too short, it's going to cost me a lot of money. Where's that sweet spot in between? Two more definitions: the defender first cost, or that's really the first cash flow for the defender, and that's the current market value of the defender. Okay, this is an installed and existing asset. So what's the market value? If I were to just try to sell it on the market, how much is it worth? That's the cost of the defender. The first cost of the challenger is the cost of replacing the defender with the challenger minus the market value of the defender. Okay, so this is well, what's the cost going to be if I've got this challenger put in place? Now, more on the economic service life. This should hopefully give you a better a pictorial idea of what the economic service life is. And it says here, the number of years at which the lowest annual worth of cost for an alternative occurs. So first, what's that cost made up of? The annual cost, the total annual worth, total annual worth of cost is depicted here in yellow. And if you can eyeball it here, it looks like maybe 9 years, maybe 10 years would be the economic service life of this particular alternative. Okay. Well, why do we have this sort of bathtub-shaped curve? Well, let me explain it to you. There's two major components that make up this annual worth or this annual cost curve. One is the capital recovery, that's this blue one going down, and the other is the annual worth of the annual operating cost, and it's in sort of magenta, and it's going up. And you add these two together, and you get this yellow curve here, the total annual worth. Okay. Well, the annual worth of the operating cost tends to increase as the asset ages. You say, why is that? Well, these things start to wear out. There's more maintenance costs. Just think of your automobile. As your car gets older, there's more maintenance you have to do, so the cost tends to rise. The maintenance cost or operating cost tends to rise over time. Also, maybe when the equipment starts becoming obsolete, you have to pay a little bit more for operators to operate it because the know-how is starting to slip away. For different reasons, though, that magenta curve tends to rise the longer you hang on to something, because it just takes more over time to operate it. On the other hand, the capital recovery cost tends to decrease as the capital cost is spread over more years. Well, you go and buy for example, again, go buy a new car. If it costs you $20,000 and you turn around and you sell it the next year, well, you're going to take a big hit because it's depreciated quite a bit. You can't sell it for near what you purchased it for. Well, you hold on to it for 20 years. Well, you may get nothing for it, but in general, it's only costing you the capital recovery is just a little over $1,000 a year. So that's sort of the idea of in a pictorial diagram of where the economic service life is, and it's at the lowest point of that total cost curve. The next slide should give you a way of putting this into engineering economy formula terms. And the total annual worth is it's the minus capital recovery minus the annual worth of the annual operating cost. It's really the sum of your costs is what it is. So the capital recovery is the first two terms of the equation here, where P is the initial investment, the current market value, and S is the salvage value. Okay, so what you can get for it. And that's, excuse me here. It's S of little k, so it's the salvage value after k years. So I really should be putting a small k on this annual worth here, AW sub k, and that's the initial cost spread over k years plus the service cost or salvage value spread back across that same number of years. So that's the capital recovery, and then the annual worth of the annual operating costs is the following. You have an operating cost each year. We'll say AOC is the operating cost each year for years 1 through k. Well, what I'm doing here is I'm doing a P given F, so I'm finding the present worth of all those. So this is the sum of the present worth of all your annual operating costs. Well, then I turn around and spread that back across the k years to find an annual value. Okay, so if you look at this, we're trying to find an A given a P. We're trying to find an A given an F. We're trying to find again an A given a P. So essentially, you can see here we're turning all these cash flows into an annual value, annual operating cost. the following is an example of finding the economic service life. And what we're going to do is we're starting out with a manufacturing process that's going to be considered for replacement. The current market value is 13,000 at time 0. The question is, what is the economic service life of the defender if the interest rate is 10% per year? And I'm giving you some additional information. The market value after 1 year, see, originally it's 13,000, and after 1 year it's 9,000. After 2 years it's 8. 3 years it's 6. Falls down to 2, and after 5 years it's worthless. Okay. The annual operating costs each year for those 5 years is minus 2,500 the first year, 2,700 the second, and you can see it's slowly growing. Okay. So to find the capital recovery costs, come down here, CR sub 1, that's the capital recovery cost if I hold on to the asset for a single year. So again, this is the capital recovery if I hold on to it for a single year. Well, it's the 13,000, it's my current market value, spread over 1 year. Again, I'm doing this for 1 year. And then at the end of that year, I have a salvage value of $9,000, the market value, $9,000, and I spread that back 1 year, or an A given F. And that turns out to be the $5,300. Now, to explain the capital recovery for year 2, it turns out I'm showing here a minus 3681. How do I get that? Well, I take that same initial, what it's worth now, the 13,000 it's worth now, but now I'm spreading it over 2 years. Okay, and after 2 years, I can sell it. The market value is $8,000, and so I spread that back. I want to find the annual worth of that future value. Okay, add those two terms together, I get the minus 3681. I use that same concept for year 5. It would be minus 13,000 A given P 10% 5 plus 0, essentially. Now I have to find the annual worth of the annual operating costs. Well, in the first year, I already have the annual operating costs, and it's for a single year, so it's just that value. However, for the second year, now I want to find the annual operating cost if I hold on to the asset for 2 years. And it turns out to be $25.95. How did we come up with that? Well, if you look back at the formula on the prior page, I want to take each of these cash flows. I want to take the 2,500, put it to time 0, so I have to discount it by 1 year. And the 2,700, I have to discount it by 2 years. Okay, so that's a P given F 10% 2. Add those together, and then I have to spread those out so that it's equal annual payments. And so I use an A given P 10% 2, and I get a minus 25.95. Now the annual operating cost for 3 years, I have to deal with all 3 cash flows. The minus 2,500, discount it for 1 year. The minus 2,700, I discount for 2 years. The minus 3,000, I discount for 3 years. So I have a present value for those 3 cash flows. And then I turn around and find the annual equivalent spread over the 3 years. It turns out to be minus 2717. Okay? And I keep doing that for 4 and 5 years. So the total annual worth, okay, for 1 year, 2 year, 3 year, 4 year, and 5 years given in the last column. Okay? And that's that bathtub curve. That's the yellow line that we saw in the prior diagram. And where's the smallest point? It's right here at 3 years. So the economic service life for this particular manufacturing process is 3 years. Now, to perform the study, okay, there's 2 types of studies. One is no study period is specified, and the other is study period is specified. We're just going to deal with the no study period specified. Here's how you perform it. Step 1 is you perform an ESL analysis on both the defender and on the challenger. What we did on the prior slide, you have to do for both the defender and the challenger. Now, if the annual worth of the challenger is less than the annual worth of the defender, and this is at its ESL, then replace the defender with a challenger and end the study. Else you go to step 3, which says you keep the defender for a year, then obtain new market value and estimated AOCs for the defender and the best challenger for the next year, and you go back to step 1. Here's an example. I've got a challenger and a defender. Okay, the challenger is a new say it's a new manufacturing process I'm considering bringing in. Its initial cost is $50,000. Okay. The market value after 1 year is $40,000, after 2 years $32,000, et cetera, et cetera. Okay, and I also list several annual operating costs. For the first year it's $5,000, second year it's $7,000, et cetera, et cetera. Okay. You don't see all the calculations here, you just see a final value. But doing like we did on the last slide, we have to find the capital recovery if I hold on to it for a single year and the annual operating costs for a single year. Those sum up to $20,000. Okay. Then I do a 2-year study. Okay. If I, what's the capital recovery for 2 years and the annual operating costs spread over 2 years, and I do that all the way up through 5 years. Economic service life of this particular challenger is 4 years, and the best value is $19,123. Now I take a look at the Defender. That's the asset that I currently have in place, the manufacturing I currently have in place. Its initial market value is $15,000. Its market value after 1 year is $12,000, after 2 years is $9,600, etc. The annual operating cost is given as minus $20,000, minus $8,000, et cetera, et cetera. And I go through that same process of finding the capital recovery and the annual worth of the operating costs. And if I held on to the asset for 1 year, it's $24,500. 2 years, $18,357. 3 years, $17,307. So the best option is 3 years at $17,307. Now, because that $17,307 is less than the $19,123, I will keep the Defender for another year. So I go through that whole exercise of a replacement study and find the economic service life of both the Challenger and Defender, and conclude, hey, I just ought to hang on to the Defender for another year. So now let's fast forward a year in the future. Okay. Now I've got new market values and annual operating costs for the Defender 1 year later. And I go through the same exercise and find the total annual worth if I own it for K years. And if I own it for 1 year, it's $23,200. If I own it for 2 years, it's $20,819. So 2 years is economic service life now for the Defender 1 year later. I have the same values for the Challenger, because I'm assuming in this case that the Challenger I could still purchase it for what I could the year before. And I come up with, again, I should be using 19,123 here as my economic service life of 4 years. And because now the 19,123 is less than the 20,819, I should immediately replace the Defender with the Challenger. And that essentially is the replacement study. You may want to pause here. And bring up the PowerPoint slide for the next chapter, for chapter 13. I am going to do that right now. Okay, I will switch you back to the computer here and begin the slideshow. Break-even analysis. Chapter 13 talks about break-even analysis. What break-even analysis is performed to determine the value of a variable that makes two elements equal. In economic terms, determining a parameter such that the revenue equals the cost. That's usually what we're dealing with in economic terms for break-even analysis. Things we tend to be studying, what's the variable that, or the parameter that we're doing the analysis against. It's typically things like production volume, percentage of capacity, labor rates, replacement costs, etc. Before I get into the break-even analysis itself, I want to define a cost function. This is very typical. A cost function usually has both a fixed cost component and a variable cost component. The fixed cost is that cost which does not vary based on production volume. It includes things like the building, insurance, fixed overhead such as an engineering staff, equipment recovery costs, information systems. It's no matter if you build one or numerous products, you've got this fixed cost that won't go away. The variable cost, on the other hand, is that cost which varies as production volume varies. And this includes things such as direct labor, the materials, warranty, utilities, marketing, etc. Typically, materials is one of the greatest components of the variable cost. Here's a pictorial diagram of the cost function. In the blue is the fixed cost component, and in the and you see it does not vary with volume. Volume's here in the x-axis, y-axis is the actual cost. Whereas the variable cost, as volume rises, the variable cost rises. And it's linear in this particular example. The yellow is the sum of the two lines, and that's your total cost curve. So again, this one is presented as a function of production volume. We could have presented it as a function of capacity. We could have presented it as a function of labor rate. But in this case, it was just production volume. Now, for break-even analysis, often we're trying to find the break-even point. And in this particular case, we want to know, well, at what point is my revenues going to be the same as my cost, or what's the break-even point? Or in other words, at what volume I must produce at some volume above the break-even volume in order for me to make any money at all. And the question is, what is that? And it's the point where these two lines cross. Okay, it's the intersection of these two lines. So do you recall how you find the intersection of two lines? Well, I'll show you here on this slide. It's really, you set one line equal to, you get a function for one line, and you set that equal to a function for the other line. And here's the example. The cost curve, I'm going to use a fixed cost of 10,000. I'm starting at 10,000, and I'm going to have a variable cost of 5,000 for every 1,000 units. So you can see I go up to 15,000 here, 20,000, 25, 30, 35. Okay, so that's my cost curve. Now my revenue curve, I'm going to assume I make $8,000 for every 1,000 units, or basically $8 per unit. And so you can see after 1,000 units, I'm at 8,000, and after 2,000 units, I'm at about 16,000. Okay. So what we're going to do is we're going to let Q equal the production volume, and that's our unknown. So QBE, well, actually QBE is this point here. And it looks roughly somewhere. It's obviously between 2,000 and 4,000, and probably greater than 3,000. So let's, and that's going to be QBE. So what we're going to do is we're going to set that total cost curve equal to the revenue curve. So the total cost is 10,000 plus 5,000 times whatever my production volume is. We're going to set that equal to the slope of the revenue curve, which is 8,000 times QBE. Okay? So now we have a single equation with one unknown. Do a little bit of algebra, and you turn out with 3.33, or 3,333 units is that point at which these two curves intersect. Now, often you also do what's called a sensitivity analysis when doing a break-even analysis, and that's sort of the idea of, if I go back to the previous slide, I had variable costs set at $5,000. Is my variable cost really going to be 5,000? Usually fixed cost is pretty easy to come up with an idea of what that's going to be. Variable cost, well, sometimes that actually varies year to year or month to month, and depending if you're having a bad month or a good month in production. So what I want to do is say, well, maybe it's not going to be 5,000. What if it's 4,000? Or what if it's 6,000? Okay, what's going to be the impact on my break-even point? And so that's what I'm doing here. Is I'm basically just analyzing from 4,000 up to 6,000 on my variable cost. Okay, I'm keeping my fixed cost the same, and I'm keeping my revenues the same. And you'll see that the break-even point, when it was 5,000, was the 3,333. But note it's quite sensitive to the variable cost. As the variable cost changes a little bit, even $500, the production volume, the break-even point goes down quite a bit. Or if I go up $500, I have to make quite a few more units to break even. Oh, here's kind of an interesting in-class exercise I usually ask people to do. You can try it on your own. If you had a starting salary upon graduation of $50,000 per year, and the state takes 6% in taxes, and the feds take 21%, and there's a 7.5% Social Security tax, and the Medicare takes another 3%. But you use good tax advice, and you're able to reduce this total by 20%. Okay, this total tax by 20%. I ask this question: how many months do you work for free? In other words, what is the break-even point in months between taxes and salary? And if I remember correctly, it's somewhere between 3 and 4 months, I believe. But you can work that out on your own. Here's another break-even analysis. This is just a break-even analysis between two alternatives. They both have fixed costs. They both have variable costs. And this comes to a question: do I go with alternative A or do I choose alternative B, or in this case, alternative 1 or alternative 2? And if you can eyeball it here, is if the demand for the product is 1,000 units a month, which alternative should you choose? So if your demand is right here, if your volume is right here, which one should you choose? Well, the answer is obviously in this case alternative 1. However, if your demand for the product is 3,000 units a month out here, then you should probably be using alternative 2. So what is the break-even point between these two alternatives? Well, in this case, you're going to set the cost curve of one alternative to the cost curve of the other alternative. And so alternative 1 has a fixed cost of $10,000, and it has a slope of 5,000. And I'm going to multiply that by my unknown break-even point volume. I'm going to set that equal to alternative 2, which is a fixed cost of 15,000 plus a slope of 2,000 as a function of volume. Do a little bit of algebra, and I come up with QBE equals 1.66, or 1,666 units. I'm going to end today talking about a break-even analysis using an annual worth approach. Okay, and here's the example. I have two alternatives exist for a machining process. Alternative 1 has an initial cost of $10,000 and a salvage value of $1,000 after 5 years. Alternative 1 also has a variable cost of $1 per unit of product produced and an annual maintenance of $1,000. Okay. Alternative 2 has an initial cost of $15,000 and a salvage value of $2,000 after 7 years. Alternative 2 also has a variable cost of 80 cents per unit of product produced and an annual maintenance cost of $1,200. So what is the break-even point in annual production volume? Assume a MAR of 10%. So again, I'm going to have to set something equal to something. So I'm really going to set the annual worth of this alternative equal to the annual worth of this alternative, with the unknown being production volume. And here we go. We're going to let X equal the annual production volume. So the annual worth of the alternative 1 was, I'm going to have to spread the $10,000 initial investment across 5 years. And then I have a salvage value of $1,000. That's in the future, and I'll have to spread that back across 5 years. And each year I have a $1,000 maintenance cost, and then I'm going to have a production cost of $1 per unit produced. So I can take that, and it reduces down to this function here. Okay, annual worth 2, I have a $15,000 initial investment. I'm going to spread that over 7 years because it has a 7-year life. I've got a $2,000 salvage value, and that occurs in year 7, so I'm going to spread that back across 7 years. Okay, and I have a $1,200 every year for maintenance, and I have a production cost of 80 cents per unit. I'm going to multiply that by my production volume, my unknown production volume. And that reduces down to the third line here for annual worth 2. Let's set those two functions equal to each other. I do that down here. And now I have a single equation with one unknown, do a little bit of algebra, and I turn out with a break-even volume of 2,980 units.
And that concludes Learning Module 13. Again, we covered chapters 11 and chapter 13 from the blank and Target text. And I'll see you again in Learning Module 14.